So in this video, we want to look at the work done by a variable force. I want to imagine a variable force that's pushing a particle along the x-axis here. We can't just multiply f by the distance because the force changes as the particle moves along here. It's a variable force. But what we could do is if we say we're going from A to B here, if we imagine another point, let's call it point C. And we find this little distance in here and we call it, it's a very small distance in x. So I'm going to call it delta x, little delta x, going from A to C. If that value is small enough, and we imagine that it's a really, really tiny value, then the work done by the force between A and C, is very roughly, almost, just got by saying that's the force times this tiny little value, delta x. And we can only do this because delta x is so small that it's almost insignificant. But if we then continue lots of delta x's in here, what we could do is we could find the total work done by adding up all of these f delta x's. So the work done by the force between A and B then, this whole section from here to here, is going to be roughly equal to the summation, add up all these different f times delta x. But we need to be a little bit careful because that's going to go from when x is A all the way up to when x is B. But that's only going to work as delta x is really, really tiny, and as it gets smaller and smaller and smaller and smaller. In other words, we want to find the limit as delta x tends to 0. As delta x gets almost infinitesimally small, then this works, that we can find the work done by the force by multiplying f by delta x and doing all the summations. And we'll have seen maybe in calculus before that this is the basis of integration, and we can then rewrite this, the limit as delta x tends to 0 of f, the summation of f delta x, as the integral between x is A and x is B of f dx, and the delta x changes to a dx. And so this then the work done is simply we integrate the force with respect to x or s, depending on what variable you're using, between the limits that you have. I have a couple of examples here. This first one, a particle mass m slides from rest down a plane 30 degrees to horizontal. The resistance to motion of the particle is ms squared, where s is the displacement from its initial position. Find the velocity of the particle when s equals 1. Okay, so quick wee diagram, just to see it's right. Here's our particle, and we have our weight going down, mg, we have our normal reaction, and we have 30 degrees. Nothing too complicated there. But the first thing that we can say, we know that the work done by a variable force is the integral of that force. So the work done here against, or the resistances to motion, is going to be the integral of, well, from its initial position, its distance or its displacement is 0. We want to work out the work done when it's gone 1 meter, so between 0 and 1. And those resistances are ms squared. And so it's going to be a ds rather than dx. M being the mass, it's just a constant. So when we integrate that then, we're going to get ms cubed over 3 between 1 and 0. And we put 0 into that, so it's nothing. When we put 1 into that, we just get m over 3. So the work done against resistance is going to be m over 3 joules. And using our work energy principle then, the kinetic energy initially plus the potential energy initially plus any work in is equal to the kinetic energy finally plus the potential energy finally plus any work that goes out. Now, the resistance slides from rest, so its initial velocity is 0, so its initial potential energy is 0. We can work out the potential energy if we use our base here, and then this distance is 1 meter. And so if we want to find the height, h, that's going to be 1 meter sine 30, or 1 sine 30, which is just sine 30. So the potential energy is mg times the height sine 30, so it's mg sine 30. There's no work put in here. We're not told about any force pushing this, so that's 0. Its final kinetic energy is what we want to find, so a half mv squared. Its final potential energy, well, we've used this as a baseline for potential energy, it's going to be 0. And any work that goes out, well, we've had to do work to overcome this resistance, and it's m/3. So that goes in there. Now, if we put this in, sine 30 is a half, so mg/2 is equal to mv squared over 2 plus m/3. When we rearrange it, we get v squared is equal to g minus 2/3. And so the final velocity there, we put it into the calculator. Remember, g is 9.8, not 9.81. We get 3.02 meters per second. Second example, a particle of mass half a kilogram moves along the positive x-axis under the action of a variable force 40/x² newtons directed away from O. The particle passes through a point 2 meters from O with a velocity of 8 meters per second away from O. It experiences constant resistance force of 6 newtons. Find the speed when it's 5 meters from O. Okay, so first we have this particle, and it's got a force on it of 40/x². And there's a constant resistance of 6 newtons going backwards. And it's going along the x-axis here. So it's going, when it's 2 meters from O, there's O, it's 2 meters from O, and then 5 meters from O. So the velocity here, v, is 8, and the velocity here we want to find out. So we're going to use something similar. First of all, let's find the work done by this force. The work done is the integral between 5 and 2 of 40/x², dx. Because we're dealing with x, we're going to integrate with respect to x. Which is the integral between 5 and 2 of 40x to the minus 2 dx, which is 40x to the minus 1 all divided by minus 1 between 5 and 2. And when we put that into our calculators, we get that's 12 joules. The work done by the resistance then is the integral. We could do it by integration, sorry, but because it's a constant force, we can simply say it's force times distance, which is 6 times 3, which is 18 joules. Now again, using our work energy principle, the initial potential energy plus the initial kinetic energy plus the work in equals the potential energy at the end plus the final kinetic energy plus any work out. Again, your potential energies here, it's along it's along the x-axis, so there's no potential energy. The initial kinetic energy is a half times m, which is a half times 8 squared. And the work put in by this force, we worked out to be 12 joules. The work out then is a half times the mass times whatever v squared is. And the work out is any work against resistances, so that's 18 joules here. This works out 28 is a quarter V squared plus 18, and we work that out to be then that V is equal to 2 root 10 meters per second.